Welcome to this explainer, where we're going to uncover the hidden engineering principles that run our modern world. It is incredibly easy to take the tech all around us for granted, but behind almost every machine making our lives easier, there's this fascinating invisible logic at work.
I mean, we interact with automated machines every single day, right? But today we're figuring out exactly how they regulate themselves. Just think about it for a second. How does a traffic light actually know when it's time to change? Or how does your AC know the precise moment to stop pumping out cold air before you literally turn into an icicle? Well, the answer is all in the elegant science of control systems. So here is our roadmap for today. Number 1, what are control systems? 2, open versus closed loops. 3, the magic of feedback. 4, how feedback upgrades systems. And 5, decoding block diagrams. All right, let's kick things off with section 1, what are control systems?
Whether we're talking about a basic home thermostat controlling your boiler or some massive industrial machine churning out cars, it all boils down to this one fundamental idea: managing inputs to control an output. Essentially, a control system directs and regulates the behavior of other devices to get a very specific, desired response. Engineers even classify them based on those inputs and outputs. You'll hear terms like CISO for single input, single output, or MIMO for multiple inputs and multiple outputs.
In its absolute most basic form, you apply a sequence of input signals, the system processes them, and out pops a controlled output. It sounds almost too simple, but the way that processing happens inside the system changes literally everything about how a machine behaves in the real world.
Which brings us to this central conflict in automation: blind systems versus aware systems. Section 2, open versus closed loops. Think about an open loop system. The output is never fed back to the input, making it completely independent of whatever result you actually want. You've got an input going to a controller, which sends an actuating signal to a plant, and out comes the result. But the system itself is essentially blind. It's exactly like a basic traffic light on a strict timer. It just runs its sequence over and over, totally ignoring whether there's a massive traffic jam or absolutely no cars at all. Now enter our hero, the closed-loop system. The game changer here is a vital pathway looping back around. It uses an error detector to constantly compare the actual output against your original input. And by doing that, it generates an error signal. So instead of just a dumb direct input, this error signal is what tells the controller how to act. It adjusts itself automatically on the fly. So the real takeaway here is the trade-off. Open loops are super economical and really easy to design, sure, but they are famously inaccurate because they just can't adapt. Closed loops, on the other hand, they're complex and definitely costlier to build, but they give us incredible accuracy. They are the true backbone of modern automation. Moving right along to section 3, the magic of feedback. Feedback is basically the secret sauce that adjusts the output automatically until we hit that precise response we're looking for. When you take a fraction of what your machine is producing and loop it right back to the starting line, you're giving the system a sense of awareness. You're allowing it to actively improve its own performance in real time. There are two major flavors of this mechanism. First, you have positive feedback, which adds the output back to the reference input, essentially multiplying the effect. But the real star of the show is negative feedback. This crucially reduces the error between the input and output. It is the exact mechanism that prevents systems from spiraling totally out of control and keeps everything perfectly balanced. Now let's see this in action. Section 4, how feedback upgrades systems. Out in the real world, machines face this constant villain we call noise. Now, that could be a sudden temperature drop in a room, friction in a motor, or random electrical interference. But a closed-loop system actively detects and fights it. If external noise plunges into the middle of your process, disrupting the flow, the feedback loop notices the disruption in the final output and immediately starts compensating for it. And feedback doesn't just fix errors either. It meticulously controls stability, making sure the machine operates safely without erratic jumps. It can modify the overall gain, cranking it up or dialing it down depending on the frequency. And it drastically reduces sensitivity. That means if internal components wear down over time or parameters shift, the system self-corrects and remains practically unfazed. When you look at the math behind it, it's pretty wild. The noise is divided by a massive factor: 1 plus the forward gain times the feedback gain. If that combined term in the denominator is a large enough number, the total impact of the noise drops closer and closer to zero. It's basically erasing the interference using pure math. Let's wrap things up with Section 5, decoding block diagrams. Think of block diagrams as a kind of pictorial algebra. Instead of getting bogged down in lines of heavy calculus, engineers just build visual models. A block simply represents what a specific component does to a signal. You have takeoff points to pull that signal in multiple directions without altering it, and summing points to bring different signals together on a collision course. A summing point is really just a simple mathematical junction. Let's walk through exactly how it combines signals based on their polarity. Imagine a summing point right in front of you. Step 1, your main command, input A, arrives with a positive charge. Step 2, your feedback reading, input B, arrives with a negative charge. Step 3, the junction calculates the output as A minus B. It's straightforward logic. If two signals enter with a plus sign, those two positive inputs add together. But if a positive and a negative input meet, they subtract to find the difference. This simple little visual node is literally the heart of the error detector we were talking about earlier. By applying these simple rules of block diagram algebra, like combining parallel blocks, shifting takeoff points, and calculating those summing junctions, engineers can condense a massive, complex feedback loop into one neat, manageable equation. You literally shrink the entire closed loop down to a single transfer function. This is a total game changer because it allows designers to perfectly analyze a machine's behavior before a single part is even manufactured. We've seen just how powerful it is to take a blind system and make it self-aware. And it kind of makes you wonder how applying a little closed-loop thinking could optimize our own daily routines, right? If negative feedback brings such incredible stability and pinpoint accuracy to our machines, where else in your life could a little objective error detection keep things perfectly under control? It's a pretty fascinating concept to chew on. Thanks for tuning into this explainer. I hope you found it as engaging as I did.